But that would be the wrong way around. Because Sean's talk follows on quite nicely from this, in the sense that I'm talking about the amount of phosphorus in the sediment and its potential, or its stability, its geochemical stability, if you like, which leads on to what Sean will be talking about next, which is about the bioavailability. So, this, I guess my background is I'm a river scientist. I've got a very similar background to AD, in the sense I'm interested in fine sediment dynamics within river systems, and often associated with the sediment comes contaminants, and in this case phosphorus. So we're quite interested in the sediment dynamics and the associated phosphorus sediment dynamics within the system. I'll give you a bit of background, and then really the two key parts of the talk are, or of the data that we've collected so far, are the spatial patterns in the concentration of phosphorus in the fine sediments in the channels. So we're looking at those spatial patterns across the 3 study catchments. And then alongside that, we're saying, well, we've got this much phosphorus in the sediment, how much could be released back to the water column? So we're thinking really, if we go back actually to this slide here, we've got a nice silted up gravel bed here, probably harbouring phosphorus. The sediment is a reservoir for phosphorus. Is it a long-term sink, or could it be a future source? That's really the sort of the management question we're trying to get our heads around. I think we've had a lot on the background catchment context. I'm particularly interested, as I said, in sediment fluxes, sources, and storage dynamics. And we've got these background sediment problems, which again we've heard I think enough about so far without me having to say more about that. Sediment's an important part of the catchment system. It's a nuisance in some contexts, but it's also a resource. I think that's often flagged up again. It's something that we do need within the system, but it's about getting the balance right. So as far as the phosphorus angle comes in, in many situations the flux of phosphorus down the river channel is largely associated with the particulate flux, and it can be up to about 90%. So 90% of the phosphorus in movement is potentially associated with sediment within any river basin. And so the sediment is very important as a receptacle for the phosphorus, and if the sediment is being stored up within the system and it's sitting around loaded with phosphorus, it could be a potential source as well. So the obvious route is through soil erosion, particulates being washed off the surface, particulates being washed off in association with livestock. And there's been a lot of work done on this, and we've got some benchmark figures down here, if you can see them beyond the little thing there. Still within the channel, phosphorus concentration typically is less than about 400 milligrams per kilogram in systems that haven't had a huge amount of or intensive agricultural impacts. We've got this nice benchmark figure of about 400 milligrams per kilogram from low intensity big farm catchments, which goes up to about 1500 milligrams per kilogram in systems that have been impacted by more intensive agriculture. This is based on a survey done by Des Walling a few years back across quite a lot of river basins within the UK. So that's quite a nice framework within which for us to compare the data we get from the talk and then to think about the context of the concentrations we have. So the other source, of course, is effluent pipes. Luckily in the talk we don't have combined sewer overflows like this. This is in Bradford, where there's been a lot of work done on particulate phosphorus within the big urban systems. This is more typical of what we get in our agricultural system, in our rural systems. But there's potential for the dissolved phosphorus that's coming out of these to interact with the sediment within the bed, within the water column, and for that phosphorus to be stripped out and stored within the sediment. So we're interested really in these two sides. We've got the stuff washing off, and then the material, the dissolved coming in, and being attached to the sediment. And those are our two end members, if you like, in terms of our how much phosphorus is within the system. I should say actually here on the urban systems, concentrations go up another 1,000 milligrams per kilogram in the literature. So we're looking at much more elevated phosphorus concentrations in sediment where you've got a large input from sewage treatment works. So this slide also shows the students about the importance of sediment. Hopefully in this slide you can see we've got big plumes. These are floods back in 2012, I think. It was the, I can't remember what time of year it was. There's some big events in 2012 that were captured by a European remote sensing website. And you see these big plumes of sediment coming out into the coastal zone. So I always like to emphasise the importance of fine sediment within these systems. It's a catchment to coast perspective. But from our point of view, of thinking about the sediment, we're thinking about the storage of that material within the system. It's stored within the channels, it's stored down in the estuaries, it's stored on floodplains, in wetlands, and that material is harbouring the phosphorus, and we need to know how stable it is. So that really brings me to our two key questions, which are quite simple questions, really, in terms of this project. We want to know how much phosphorus is held by the sediment stores within the system, what's its concentration, we can compare it to those literature benchmarks, and then we need to know whether it could become a potential future source of phosphorus to the water column. Those are the two main questions. So the sampling design is similar to what we've seen in some of the other studies. It's a spatial approach, so we've targeted the mainstream networks and largely driven, we tried to get good spatial coverage. Access is obviously important, but these red dots represent where we've been in and collected silt from the channel bed. And the method we've used is a stilling well method. It's a drill with a mixer on the end, and it just mixes up the gravels and all the fines come out into suspension. And then we fill up a bottle, take it back to the lab, decant it and freeze dry, and we end up with a powder. We sieve that powder down, so we're working with the fines, less than 63 microns, so we're working with the silt and clay fraction, and that material then goes forward for the analysis. So I guess quite an important limitation of the approach is that we're looking at concentrations of the silt on the gravel bed. The missing factor is we don't know how much silt is in within the beds, and that's something we're going to be working on over the summer. Very, very difficult to quantify. As you can imagine, it's highly spatially variable. But that's another element to the work that we're going to try and get our heads around. But we'll stick with concentrations for today. And this is for the winter period as well. We've done the winter sampling and we've also got a set of data taken in the summer, and we'll be comparing those two. So this is the lab, just to give you a feel for the kind of things that go on. There's Rupert, who's in the audience. He's done most of the, I should say Rupert's done most of the sampling analysis on this project, along with Matt, the master student, and Emily, who you'll hear about more from Sean later. Grinding the soil up, we then pack it into these little pots and measure it on our X-ray fluorescence instrument, which gives us major and minor element geochemistry, including phosphorus. And so what that gives us is a whole suite of compositional parts of the sediment, and it allows us to get some idea of the relationship between phosphorus and other components of the material. And then also alongside that, we've done acid digests and analysed the acids which we digested the material with for phosphorus, as we've got a wet chemistry method alongside the dry method as a bit of a quality control check. And then the final step is that on selected samples we've done sequential extractions, which is basically where we take a series of extractants of increasing strength and we shake the sediment up in it. And what happens is that the phosphorus is liberated, and each step we just hit it a bit harder. So it gives us a sense of how easy it is for the phosphorus to be released from the sediment and under different environmental conditions. So I'll be able to give you some data on both these aspects now. So this is we've got our study site up here in the upper part of the study area. And what we've got, hopefully it's clear enough, on the scale here we've got the blobs represent amounts of phosphorus within the sediment. So the big blob here is 4,000 milligrams per kilogram, and the tiny dot is 500 milligrams per kilogram, underneath which, according to the literature, we're looking at very low systems. The first thing to know is that all of our blobs are bigger than that baseline, so it's what we'd expect. Most of the system's been impacted by additional inputs of phosphorus. And generally speaking, they're fairly consistent within these systems. We've got a little bit of a hotspot up here, but there's no real spatial footprint. So this area here was quite popular with cattle around the time of sampling, so we've got some kind of a localised impact there, but we don't really see any indication of that downstream. So, so this is in the Huntscott, Little Dart, and then we'll move down now to the Dolch. So in the Dolch here on the same scale, and as you can see the blobs are a lot bigger, they've got two colours to them. The reason being that we've had a bit of trouble analytically here. The uncertainties on these have been quite high on the XRF, so something's interfering with the XRF signal. So we're getting values, but the instrument's retaining quite high uncertainties. So they're way up in the sort of the 2 to 3,000 mark. This one down here is a bit more consistent, and you can see that the bottom end is elevated to 2,000, and these upper ones are pretty high as well. So what we're suspecting, what we're hypothesising here, is that because there's not any obvious point sources, that there's some kind of an agricultural input, maybe a lot of surface soil erosion from cultivated land. Potentially it's a hypothesis, so I think when these results come through, it'd be interesting to see how those two things cohere. But it's certainly elevated and consistently elevated within this stream. And then onto the Tor. So we come down off the moor, where it's, as we'd expect, pretty low. We've got a little bit of a blip here around Stickle Path, then it drops down again. We reach North Taunton, where we have the largest concentration we measured. And this is at the just downstream of the works and the sewage treatment, so the dairy and the sewage treatment works. And from then on, we have this elevated concentration compared to the top here, and there's a statistically significant difference between the north and the southern part of the stream. And so we've got another hotspot, here a hotspot with a limited spatial extent, and here a hotspot with a more extensive spatial footprint. So it implies that the point source here is having an influence on the sediment silt concentrations. Okay, so that's the spatial patterns, so that's the winter. We're going to have the summer to compare to that. This is the results from the sequential extraction. And what we have here is an increasing, I guess increasing strength is probably the best way to say it for now. We go from water-soluble P to loosely sorbed P, so these two really are what we could consider to be the chemically available components. And together those two tend to be, there's this here and here, they tend to be about 15% or less across all the sediments. And what we were quite struck with is that across pretty much all of those systems, apart from two of the hotspots, which I'll look at in a minute, the partitioning of the phosphorus geochemically is very similar across all of the system. The next one, the big green one, is phosphorus that's likely to be associated with iron and aluminium and humic substances. And this represents a huge part of the phosphorus within the sediment, so it's bound to those components. And then we move on to the less available components and finally the residual component down here. So I think the two key things, 15% is geochemically available, and then we've got this big component that's actually iron. The two sites that are flagged up here, the one on the left is the one at North Taunton, where we've got the sewage treatment works and the dairy, and we can see that the iron associated component is larger here. And that kind of makes sense if you think about iron as a water treatment component. And the other one was the well where we had the little bit of cattle stomping ground up on the top of the was at site LDO1. I can't remember the stream the first slide I showed you. And what's interesting here is that we've got a bit more associated with the iron here. The XRF chemistry shows us that we've got a lot of iron in the sediment there. There's some natural iron seepage within the system. So the sediment chemistry itself is quite an important component of the story in terms of how the iron is being bound. But we've definitely seen some kind of a human influence, I think, in these samples here. So the implications of this, I guess, are that we've got elevated phosphorus across the system, which is kind of what we'd expect. We've got our hotspots, we've got the importance of iron. What it means is that as that material moves downstream, if the environmental conditions of where the sediment is stored change, and they act to liberate the iron, then they're going to liberate more phosphorus. And so classic conditions would be where the oxygen status of the sediment is reduced, and the iron dissolves and the phosphorus will dissolve out with it. Now, as an analogy, or as an example of where this has happened in the past, this is a floodplain in Denmark where I've done a bit of work, and what's happening there is that they're wetting up the margins of the channels. This used to be agricultural land, it was heavily fertilised. The iron in the soil the phosphorus is attached to the iron in the soil very strongly, and what's happening now is they've built these big margins in, they've raised the groundwater within those margins, it's saturating the soil, and the iron's being released and the phosphorus is being released with it. So there's I'm not saying that's what's going to happen in the Tor, because we're not planning to wet up large areas of the Tor margins. What it shows is that when the sediment comes downstream, holding onto the iron nicely, if it ends up in somewhere that's a little bit anoxic, or it goes anoxic in the bottom sediments, there could be potential for release. So it's something to bear in mind. And so that's really from the kind of geochemical perspective, what about the Bartik processes, and that's what Sean's going to talk about next. So to summarise, which I probably have done already, but just the points are up here. Generally speaking, we're looking at above that baseline concentration of 500 milligrams per kilogram, which is what we'd expect. But the ranges do fall within the literature range. We don't tend to go much higher, apart from the Dulce, which seems to be a bit of a hotspot. But we do have some analytical investigations to do there as well. The known point sources, we've got this very extensive spatial footprint from the point sources in North Taunton. So it kind of corroborates, I think, a lot of what we've heard today about that particular site. And the fact that the sediment's holding onto it and the sediment is resident within the system is quite important, because we've got this association with the iron, so we need to think a bit about the chemical states of the sediment and the riverbed. And that leads us on, I think, to where Sean's going to take us next.
Brilliant.